recording. Yeah. Okay. So thank you, Pavan, and thank you to the Max and others at University of Auckland for organizing this session and the group in general. So what I wanted to talk about today was how to add a uniaxial material to OpenSees. All right. Yeah, so I planned to, I didn't make any slides, but I did prepare this Jupyter notebook, and I want to kind of make it kind of not really interactive, but kind of just walking through the Uniaxial Material interface, and then showing you where some of the resources are for how to compile Uniaxial Materials, and then actually compile it here during the session, and or compile a new material during the session, add it to the interpreter, and then run a couple basic test cases, through this Jupyter notebook here today. Okay, so just a little bit of background. Uniaxial materials are used across a wide variety of contexts in OpenSees. All right. Okay, so four things I could think of where Uniaxial materials are used are, truss elements, kind of the OG elements within OpenSees. All right, and then of course within fiber sections. All right, and then as also within sections, but as section aggregators, like aggregated force deformation responses, and then Uniaxial materials are also used in zero length and two node link elements, and a few other elements as well. Okay, so there's no like inherent units or meaning of the input and output for uniaxial materials. All right, so the calling object determines the meaning. All right, so like for truss elements, as a calling object, the trusses view uniaxial materials as being stress-strain relationships, and then the truss elements, multiply stress-strain response by an area, to give you force deformation response for the truss. Okay, fiber sections, also interpret uniaxial materials, and then use a fiber area and a location to get stress resultants, from a fiber discretized cross section. And then the section aggregator uses or interprets uniaxial materials as a section force deformation relationship with no area or anything at all. It's just straight to moment curvature, straight to torsion, twist type relationships. And then zero length and two node link elements use use uniaxial materials as force deformation or moment rotation. Like so, as like a spring, like a flexible foundation, or a PY spring, QZ, TZ, and then moment rotation, like with the concentrated plasticity type models. It's all zero length moment rotation type stuff. Okay, so but a uniaxial material is a uniaxial material. It's just a function given an input of strain, deformation, or rotation, give an output of stress, force, or or moment. Okay, so I went searching for, and I know that I wrote like how to add a uniaxial material in OpenSees, and that was almost 20 years ago, and really not much has changed. All right. I don't know if that's good or bad, but here it is, right? Here's August 2001. It kind of goes. This is a document that Greg and I wrote on adding uniaxial materials. Okay, and it's like 20 pages long. Most of it's still relevant today, but there's a more recent guide to adding uniaxial materials, which Frank put on the OpenSees wiki page, and that's here. All right, it has a few updates. All right, and he's referring to this elastic PP CPP file, which I'll show you in a few minutes. All right, but this also walks through, the implementation of that elastic perfectly plastic material, and then some other items there. So those are like the two main resources, and I think you can find some other stuff on YouTube. Some I'm sure is good, others maybe not, but I mean it's YouTube, right? But the document that Frank had from 2013 is based on this template Uniaxial Material, which is available on GitHub. All right, so if we click or go to GitHub, right, there's, or I'll go up a couple directories, but there's this, OpenSees developer directory that has core element integrator material recorder system. So it kind of has some templates in here for different things you may want to develop and add your own code to OpenSees. So if you go into material, there's some C and Fortran stuff, and then C++, all right? And in C++ is elastic, perfectly plastic, CPP, okay? And you can view if you haven't done this before, you can view source code on GitHub, all right? It's even pretty printed with the colors and everything. But this is what Frank's referring to in the wiki page, all right? But it's just an elastic perfectly plastic implementation, all right? Just like the elastic perfectly plastic material that's already in OpenSees. Okay, so I'll grab these files in a minute, all right? But today's objectives, all right, with that brief background, is to compile that elastic perfectly plastic CPP file into the OpenSeesPy module, all right? And I'll use Visual Studio to do it. And then in doing so, kind of go through the required Uniaxial Material methods. So each Uniaxial Material has to implement certain methods, all right? And then in this notebook, Jupyter Notebook, test that material using some Python commands. Okay, so if we look in, so this notebook, right, is in my Win64 bin directory, right? Here's the notebook right here. I'm running it. Down here is OpenSees.pyd, which is the Python module compiled from Visual Studio, which I last compiled 2 hours ago. Okay, so if I import, it's in the same working directory as the notebook. So if I import OpenSees as OPS, everything's fine, right? And then I want to define some material parameters. This is going to be like an EPP material. So let's say 50 KSI steel, 29,000 KSI for E. I'm just defining those as Python variables. I'll run those. And now I want to attempt to create that material. Of course, this isn't going to work, right? But yeah, you get warning, elastic material or elastic perfectly plastic CPP is an unknown type. Okay, so let's make it known, all right? And let's compile it into OpenSees. So I'm just going to go through these 3 steps. First, I'm going to grab those 2 files, the eppcpp.h.cpp from developer material CPP, and put them into my source material Uniaxial folder. Then I'll compile it in Visual Studio, and then we'll add the commands to the interpreters. All right, so kind of 3 steps. All right, so I will switch sharing. I sometimes have issues with Zoom when I switch sharing, so if I suddenly log off, or if I get booted, you'll know why. But here in my OpenSees directory, right, I'm going to go into developer, material, and then CPP. I'm going to just take these 2 files, copy them, put them in source material Uniaxial with the 85 other Uniaxial materials that are available in OpenSees. All right. Some of them are actually duplicates, but I believe, I'm pretty sure some of them are duplicates, but at any rate, those two files are there. Okay, so and then I'm going to go to add those in Visual Studio. Okay, so I'm going to switch share and go over to Visual Studio. Okay, this is the original elastic perfectly plastic material, which EPP, CPP is based off of. I'll just get rid of that. But if you go to, the material projects, Uniaxial, you just add an existing item, right? And you would find the files that I just added, all right? All right, and then let's just try to compile that project. It should compile those two new files. Yeah, that's succeeded, all right. And then we go to OpenSeesPy, and I'm going to build that. All right, so I can't open this file because it's in use in the notebook, right? So what do? Let's just stop this kernel. There might be a better way to do this, but just rebuild. Oh yeah. Erkin, you're ahead of me. All right, I'll get there. All right. Yeah, so that succeeded. All right. And yeah, so as was pointed out in the chat, all right, we need to add the commands to the interpreter. All right, so it compiles, right? But here we need to, so we did, let me get the laser pointer again. We did this, and now we need to add the commands to the interpreter. Right, this is the important part, because otherwise, just because you compiled it in, just because it compiled doesn't mean it's in the interpreter, right? So we still get that error that it's unknown, right? So, all right, so that's because we need to tell the interpreter, hey, recognize this this material. Okay, so in Python, right, you would go into source interpreter OpenSees Uniaxial Material commands.cpp. All right, in Tcl, you would go into source material Uniaxial Tcl model builder Uniaxial Material.cpp. Okay, so, and you would just cut and paste some stuff. It's a pretty easy process. All right. Okay, so if you go into OpenSeesPy, OpenSees Uniaxial Material commands, all right. I'm just going to, yeah, all right, I'm just gonna copy this stuff. Or well, let me, before I do that, sorry, I'm a little bit ahead of myself, but if you look in elastic pp cpp, which is this file here, there's this function right here, elastic or OPS elastic perfectly plastic CPP. This is where all the parsing happens for both Python and Tcl. All right, and what it's doing is just reading the input. All right, so it reads an integer as the tag, and then it reads two doubles, which is the elastic modulus and the yield strain. Okay, and then it creates the new material. All right, and then returns that. This is a void star function, so it just returns, you can return whatever you want in this function. Okay, so we need to make those interpreters call this function, all right, which is what I was about to do before I showed you this function here. Okay, so Uniaxial Material. So I just need to declare that function, right? Elastic PP. Let me make sure I wrote it properly. Elastic PP, CPP. All right. It doesn't have material on it. Okay. So just do that, and then just add it to this map here. All right, and then this thing in quotes right here is whatever you want to call the material in your input files, right? So you can call it whatever you want. You can call it, yeah, anything. Okay, so that should be all you need for Python. All right, and then for Tickle, the file is actually back in the material project in here. Tickle model builder Uniaxial material command. Okay, so I'll just search for elastic perfectly plastic, right? So you would just do the same things here. Change that. Oops. And then just add another one of these, right? For whatever you want to call that material. Elastic PP, CPP. And then you just call that function. Oops. Okay, so, and I think that's it. All right, to get it to compile and then link into your scripts. Okay, so let's build. I didn't rehearse beyond this point, so hopefully everything goes smoothly. So that one worked. Now let's build the Python module. Oh, yep, and I need to close this or stop the kernel. Restart. It's just whenever you load the module, it's like I'm running it's running in its own little server locally, right? So I can't write to it if it's in use, right? Let's see here. What did I do? All right. Plastic, CPP. The OPS Expo parts. All right, Erkin is helping me out. So you're saying in the Uniaxial material. I think I know which part you're talking about. This stuff? Let's see. Sorry. Yes. Okay, so let's try this again. And before void. All right, what did I do? All right. This? No. Yep. At the end of Huh. Sorry, I have a backup plan. Oh, that. Okay. Thank you. Thank you. Let's try this again. All right, Erican, thank you very much. All right, okay, so that worked. Let's see. So then you can cut that out of the YouTube part, right? Let's see now back to this. Okay, so now if we've recompiled it, we have a new PYD. All right, there you go. So now it's loaded. It's outputting a little print statement from Frank. You know, use at your own peril. All right, but yeah, it successfully compiled in. All right, so that worked too. Okay, so yeah, so you know within the so we got it to compile, right? So now again, thanks to Erican. It could have been a very long. I may or may not have figured that out on my own, but I'll send Erkin a big thank you. Yes, so let's see. So within the so at this point, you know, you have everything compiled, right? You don't want to do elastic perfectly plastic, right? That's already been done. You want to write concrete 23 or 24 or steel 08 or 09 or whatever, you know, whatever material you want to add. So you'll like go in to these functions, right? And you can, you know, change the class name, do whatever you want to do, right? But you know, you'll in let me go to so in your header file, right, for your material, right, you're inheriting from Uniaxial Material, and this is, you know, this will be concrete 23, 24, steel 8, steel 9, all right, and you're gonna, you know, you have constructors, right, which take
we can't
the
see your screen.
oh yeah, sorry. Okay, so here's the header file, right? So then you will you know, change this class name to whatever you want it to be, you know, concrete, steel, all right, and then you'll define a constructor, right, which will just be the name of the class, all right, and the tag, the whatever parameters it takes in, destructor, and then there's, you know, 5 methods right here that are the state determination, right? So there's set trial strain, which takes a strain and a strain rate, and by default the strain rate is 0. So if you don't pass a strain rate, it just comes in as 0. And then get strain, not too important, but then get stress and get tangent, all right, are the 2 main functions that return, you know, the stress and then the tangent for the uniaxial material, and then the get initial tangent, which is called for forming initial stiffness. Okay, so every material has to implement these methods, right? And then commit state, revert to last commit, revert to start, or for like path dependency, going from one step to the next, committing your history variables to be on the path of the solution. And then there's, so, you know, every material has to implement these, all right? And then there's get copy, which is basically telling them, it's asking the material to return a clone or a copy of itself, all right? And then send self and receive self, which are used for the databases and parallel computing, where the materials send themselves back and forth over channels so they can replicate on different processors, and then a print statement, okay? And then there's private data. So this is where you just store all the data or declare all the data that you need to define the material. All right, so there's properties, you know, yield stress, positive, negative, initial strain, the elastic modulus, and the plastic strain at the last commit. Okay, so and then trial strain, trial stress, trial tangent, and then committed strain, stress, and tangent as well. Okay, so you know, that's, you know, all the implementations are in the CPP file. All right, so there's the constructor, default constructor here. Destructor doesn't do anything. Set trial strain does a little return mapping algorithm. of course, concrete 23 will be way more complicated than this, all right? Stress tangent are just computed up here, stored as variables within the class, and then returned right here. Commit state is just updating the plastic strains, or singular plastic strain. Okay, and then just writing all the current trial values into the committed. All right, so commit state's just swapping stuff around. Okay, revert to last commit just puts the stuff back, the last committed, into the trial. Revert to start just zeroes everything out. Okay. All right, and then get copy, right, is just returning a copy of itself. All right, so just calling the constructor and pulling it back to return. And then send self is just jamming everything into a vector. All right, the tag, the properties, the committed history, and then sending it over a channel. All right, receive self is just receiving all that stuff, right, and then putting it into the automatic variables for the object. All right, so just reading and writing in the same order. Send self 0, 1, 2, 3, 4, 5, 6, 7, 8, and then writing back in the same order. Okay, and then print. Okay, so really not much to the Uniaxial materials, but they do most of the work within OpenSees for a variety of applications. Okay, so with all that, once you've coded your material, right, you're going to want to test it. All right, so this is like one of those cooking shows, right, where like you make the dish, all right, and then you put it in the oven, and then in the other oven, the Cornish game hen is already cooked, and they pull it out, and it's already cooked, all right? It's already done, right? So, but there are a lot of time elapses between those two things. Same thing's happening here, right? So, say you've programmed your material, all right? You've called it whatever you wanted to call it, all right? Then we can start to test it, all right? This is where the hard part begins, right? Is the test. Writing the code is easy. Testing it and debugging it is hard. All right. So I'm going to use NumPy and Matplotlib to do a few things here for testing. All right. So first I'll define a strain history just using the linspace function from NumPy, very similar to linspace from MATLAB. Okay. But just creating 100 points from 0 to 5 times the yield strain, where the yield strain was defined up here. All right, notice these are integers. All right, in Tickle, this would give you 0 integer division. Right, Python 3, it does floating point arithmetic for you. Right, if Sylvia's out there, that was for her. Okay, so at any rate, from 0 to 5 times the yield strain, 100 increments, all right, and then going from positive, going from that point back to negative 5 times epsilon strain at 200 points, and then going back to 0 again. So just going through one cycle, okay, and I can plot that, right? It looks like this, right? Okay, so just one strain history there. Okay, so there's a couple ways you can test Uniaxial materials. All right, one is probably a whole lot of people don't know about it. All right, but Frank added these many years ago. But there's this Uniaxial material tester. All right, it's not just a Python thing; it's also available in Tickle. But what you do is you define your material, and then you call this test Uniaxial material, right, with the tag of the material that you defined. Right. Then there's like 3 functions that you can call, all right, to just drive strains into the material and then get back stress and tangent. Okay. So set strain, all right, with the strain value, and then get stress and get tangent. All right. And it just all goes back to this test Uniaxial material. Very useful little thing. So you can just drive any strain history you want into it and get the response. Okay, so this loop, right, is just looping through the strain, which I defined up here in a vector strain. All right. So for each epsilon in strain, set the strain, get the stress, get the tangent, but I'm not using it, but it's just there to remind you that that function is available. And then plotting strain stress, all right, the stress strain history. All right, so this is EPP. You're going through one cycle. It should just do one hysteresis loop, right? And boom, there we go. So it gets up to yield stress of 50, all right? And starts here, goes there, unloads, reverse loads, unloads again, goes to there, okay? So that's not all the testing you would need to do, all right? But that's that's a start, all right? You can also, as I alluded to initially, right, you can use Uniaxial Materials and Truss elements, all right? So you could define a model, right? One dimension, 1 degree of freedom. You may not have known that you can do that, right? But you can do just a simple 1D model in OpenSees, all right? But the length of the truss, I'll just say it's 80 units, all right? So node 1 at coordinate 0, all right? And then fix it, all right? Node 2 at coordinate L, all right? So again, it's all 1D, right? So only have to fix 1 degree of freedom there. And then define our material, which we just defined, right? Or just created. And then create a truss element, right? With tag 1, node I, node J, cross-sectional area 6, just a number, right? And then the material tag of 1, which goes to here, okay? And here I'm defining a path time series, all right, with just the strain values from up above, but I'm just playing some games here and just multiplying by length to make this deformation, all right? So the truss understands it as deformation, all right? So we're just gonna take the truss and just move one end, all right? And then pattern, and then single point constraint, node 2, degree of freedom 1, reference value of 1.0. It's going to get multiplied by these values in this vector here. Transformation constraints, UMF pack, load control. I know that sounds odd, right, to do load control with imposed displacement, but that's how it is, I guess. And then static analysis, number of steps, and then here's a loop, right? Analyze, get the reactions at the fixed end of the truss, and then get the force displacement relationship or load displacement relationship and plot it, right? So that stress strain relationship goes from stress strain into force or load displacement for the truss. All right, so the yield stress of the material was what, 50? The area of the truss was 6. All right, so the yield force is 50 times 6 or 300 units. And then it goes through, the same hysteresis, right? Okay, so, there's other ways to test the materials, all right? But these are, two kind of basically doing the same thing, all right? But you want to test it as a standalone kind of stress strain relationship first, right? Make sure that works, and then make sure that it works when you use the material within the various contexts in which they can be used within OpenSees. So like a truss, that's the easiest. Zero length element would be pretty easy to test as well. All right, and then you could start doing section analysis and other stuff, if that's the route you want to take with your uniaxial material. Okay, so any questions? I guess we have time now. You can email me or visit the blog where some of this stuff has been addressed. And also a big thank you to Eric and I can't do the Turkish letters in here, but this will become part of the permanent record, right, Pavan? I'll send you this notebook, and then it'll be in there. Okay, so I think that's it, and yeah, I guess we have time for questions.
Thank you for the presentation and going over the whole process. And thank you, Eric, as well. for helping out. And yeah, now guys, questions. Do you have any questions? No questions. Wow.
It's so straightforward that it's yeah.
So if at all we have to do like concrete 23 or concrete 24 material, like you said, what kind of I mean,
like what would be different or
yeah, how you said it's gonna be complex, right? So like how complex is it gonna be, like, or what will be the difference?
yeah, so like let's just look at let me bring up one of the other concrete materials.
Yeah, that would be awesome.
So there's like concrete 07, right? So like here's its constructor, right? It takes a tag and then concrete strength, strain, modulus, tension strength. I don't know what all these things are, but whatever, however many properties there are, right? And you see it also, declares the same functions, set trial strain, or set trial is an optional method that the fiber sections call, so that you don't have to like call 3 functions to get the stress and tangent. You can just get them all in one function call, because when you're down at the level of fibers, you want to be as efficient as possible. And more function calls equals more computation time. So this takes a strain and then returns stress and tangent. Okay, that's a handy little function to keep in mind, actually. So, but then get stress, get tangent, commit state, all the same stuff, right? As we saw before. Then if you go into the CPP file, right? So here's the input function.
Sorry, what is the difference between 2 files? Like one is H and one is CPP. Can you? Sorry.
Okay, so
telling you for this.
Okay, yeah. So all right. So the H file just declares the class, right? It just says this is the class name. Okay. This is what it's a subclass of. And then here's all the public functions that any other object can call and then get some information, right? And then here's the private data that no other class can get to. It's like its social security number or whatever, credit card number. Nobody else can get it, right? Only you can use it, all right, to do stuff, all right? So, like this, concrete 07 has, the properties, some of the variables for cracking and stuff. History, there's a lot of history variables, right? Converged as well as trial, right? And then there's even some internal functions to quote unquote make life easier, right, as is commented here, right? So that's just all private stuff. So only concrete 07 can call these functions on itself, right? But any function like fiber sections can call get stress, get tangent, right? Because they're public, right? And then the CPP file defines all those functions that are declared in the H file, all right? So, but this is the parsing command for Tickle and Python, OPS underscore, right? And it's just reading in all the data, right? So, the tag, the parameters. So integer, it reads in 8 doubles, and then it just passes everything into the constructor, right? Which this all just goes down to here, does all this stuff, right? But, if you look at like set trial, just the functions get more the definitions get more complicated, right?
Yeah, that is where I'm trying to understand where is the part where we actually give it to ask, like, follow this stress strain or whatever for the uniaxial material in this.
You mean for the, well, like, okay, so here.
I mean, we are asking pretty much Uniaxial is like follow a path, right? Like follow this
Yeah.
path. So I was just trying to see where is the function or the equation in this whole big piece of code, or how are we asking to implement that?
Yeah, it's all in gets, if I understand correctly, it's in get stress. This is a very long function here. Okay. Oh, okay. Well, these just return it. So there's in set trial strain, I think is where all the computation is happening. Right?
Oh, okay.
So that's strain and strain rate, and then what calls this? Then it calls this private function determine trial state, which is probably that very long function I just was looking at. Yeah, so here it's going through all the branches and logic of.
Okay.
Yeah. But then, if you look at, let's say, like fiber section, right? So it's like somewhere in here, like fiber section 2D, it is, sorry, let's see. Yeah, so it's looping over the fibers, getting the material pointer from an array of pointers it uses. And then right here, it's calling set truss. So it's passing in a strain, which it computes here. Plane sections remain plane, right? Like epsilon 0 minus y times curvature, right? And then it's returning the stress and the tangent. And then it's using the stress to get the forces, right? And then the tangent to get the section stiffness, right? So yeah, and then, Truss has similar things, and zero length and all that stuff has similar calls. So yeah. Okay. Looks like I have a question and a.
Oh, sorry, Erican had a question.
Oh.
Sorry, you can go.
Okay. Do you hear me?
Yes.
Okay. Maybe it's not related with our presentation, but I just wonder what should we do to make our code public and available in the next version of OpenSees?
Okay. So yeah. So let's see. So like if you, so that's a good question. So once you finish writing your material and you want to add it to OpenSees,
yes,
like what the process would be. So like actually before you add the material, it's very obscure, right? But if you plan on collaborating or using as your base, highly recommend you fork this repo. So if you have a GitHub account, right, you'll need to fork the repository, which means you'll have your own kind of version of the repository downstream from this. And to fork it, you would come up here, when you're logged into GitHub and hit the fork, right? So it says I've already done it, but I could fork it into a different account if I wanted to. But if you haven't done it, this would look different, right? And then you have your own fork or branch of OpenSees, right? So like this is OpenSees, right? So if I go to my GitHub account, right, this is my fork of OpenSees, and it looks the same, but it actually has some differences between, you know, what I've added to OpenSees and then what I haven't done, or what's in OpenSees and what's in my fork, and they're like two different versions. But to get those synced up, right? Once you've like added your material, you tested it, you've committed it to your repository, your forked repository of OpenSees, right? Then you would create a pull request, okay, and you would do new pull request here. Actually, yeah, you'd want to do it in your fork, right? I'm sorry. Yeah. So here, back in your forked OpenSees, right? You would have do a new pull request. It'll ask you like which files you want to put in the pull request, and then once you do that, Frank and I will get notified, and then we'll look it over. And but yeah, there's a lot more to it than that. But if you have any problems with it, just let me know, and I can walk you through it in more detail.
Okay, thank you.
Okay, thank you.
So just to add to this question, how do we check if this part of code is compatible with the rest of OpenSees and all at our level before sending it to you?
Well, if it's well, I mean, if you keep your fork up to date with OpenSees, you know, you shouldn't run into any like compatibility issues or anything. GitHub does a pretty good job of like managing all the different branches and versions. Is that kind of?
I'm asking compatibility within the OpenSees, like when we are running, if it is running with, for example, if it's running, my Uniaxial material is running with certain elements, but not like every other element. Do we encounter those kind of issues, or like?
So I think what he's asking is what level of testing do we need to do on our Uniaxial material before we should submit the pull request? Like, do we need to do it across the entire range of elements? How many different loading protocols should we evaluate? Like, how rigorous does our material testing need to be?
Based on prior materials, not very rigorous, but yeah, it's, you know, usually you have a very specific application where you want to use the material, right? So like, be it in a fiber section or like in a zero length element or something. So, you know, definitely you'd want to test it in those, with those elements, or in the fiber section. And then, yeah, but there's not really any protocols, unfortunately.
Because some materials definitely work with static pushover and all this, but once dynamic comes, we have like huge convergence issues and all that stuff, right? So
yeah. I mean, there's, you know, you can like check for things like quadratic convergence if you're doing like with the fiber section, and you want to, you know, make sure you have the tangent coded properly, that kind of stuff. But yeah, you know, definitely for like, you know, like cyclic loading, and then, you know, if it works for cyclic, it's going to work for dynamic, because there's really nothing special about dynamic versus cyclic at the material level, unless you have like damping or something, or it's a damping material, you know, some rate dependency or something. But yeah, no actual protocols, yeah, or anything.
To implementing some type of standard, or is the material pre-specified? Is that why there's no standard protocol?
Could you repeat the first part again, or?
I'm just wondering if there's been any thought to developing a standard protocol for people who want to put their materials in, or is it too few and far between, or are the materials too specialized? Or...
Yeah, sometimes it's too specialized because a protocol for one material may not apply to others. But you know, Frank and I are starting to require people to give an example and documentation for their materials before we accept their pull requests. So that'll at least, because I mean, a lot of Uniaxial material, or a lot of materials and elements in OpenSees were put in with little to no documentation, right? And we don't know if they even work anymore, and if they don't, we don't know how to fix them, but now, here in the 21st century, right, we're requiring people to give us some documentation and examples. That hasn't always happened in the past, but no protocols in sight, but because again, I think it's, especially with the Uniax materials, because they're so diverse, it's kind of hard to have one size fits all kind of approach on that.
And we have another question from Faisal Rahman.
Uh-huh.
Faisal, you want to speak out, or should I read out?
Well, I have typed in a chat. Is there any documentation explaining the code part of the material? Like
Okay, I see.
State variables, functions.
I think in this, if you look back at these two documents, they have some explanation that you may be looking for. This one it goes into a little more depth on what all the different functions do, and then in terms of the setting of the trial strain. Is that kind of what you're asking, or?
Yeah, something like this, as well as some example from research paper. If we have some research paper and there is some explanation of material model, and it is implemented in OpenSees, so is there any documentation of that?
Not really. You mean like for the different Uniaxial materials and documentation of their inputs and outputs and everything? Or... There's not a lot of documentation with OpenSees, to be honest. But you could probably find some stuff in different journal papers, for different material models, but not in a way that's useful, I don't think. So yeah, it's like I have no idea what Concrete 07 does, or many of the other materials. Some of them are, they may have references within the source code, but and the wiki, OpenSees wiki page, OpenSees documentation usually has some documentation of what these materials do. But
so another kind of basic question, I guess.
Yeah.
What level of expertise do we need, like in C++ or Visual Studio, so that like if we want to just go and make our own material and test it, to do this process? Like, do we need to be, I mean,
I think to just like copy the files and change the class names and get it to compile is pretty straightforward. And then, you know, knowing like basic statements, but there are some subtle things with OpenSees that, or subtle things with C++, sorry, that if you're not aware of them, they may cause problems. But you know, I would recommend just kind of copying what's in that developer directory and then starting from there. But yeah, like for instance, you know, like this right here, this says static vector data 9, right? Like, you know, static means static has a certain meaning, and you don't have to have static there, but there's a reason for it. But yeah, I'm trying to show an example or give an example of one of the subtle things with C++ that, you know, may cause problems, but really at the Uniaxial material level, it's all very algorithmic and just number crunching. So there's not a lot of things going on. But if you got into the higher level stuff with elements or algorithms, it would be more complicated.
Adding an element or something would be the same process, or is it good? The process wise, is it going to be different, or like is it going to be the same if you want to add an element?
Yeah, it'd be a similar process. Let's see, if you go into developer element, like there's a truss element, right, that you could, this might be too simple to start with, but you know, it's kind of the same thing, right? Like there's an OPS function, and then you know, read the inputs, and then there's, you know, certain methods you have to implement to get the force and stiffness for the element. Yeah, but then you have to deal with nodes and like going out to nodes and getting displacements and stuff. Yeah, but yeah, I mean, overall it's kind of a similar setup to the materials, but a little more indirection is involved.
Okay.
Yeah.
Do you guys have any other questions? Anyone online has any questions?
I just wanted to say hi. This is Sylvia. I made it to the meeting just now.
Oh. Hello.
Over to the recording. Hi, Mike. Sorry
Hello.
about
I picked on Tickle a little bit. You'll have to watch the video to see.
I'll be, if you hear me shouting at my phone, it will be when I'm watching the videos then.
Okay.
I mean, any other questions, guys? No? People online?
How many, maybe like just raise your hands virtually, but how many people know C++?
I know how to copy and paste existing C++.
Okay.
Yeah, never worked on C++.
Yeah. Okay. Yeah, I mean, it's not, Faisal knows some C++, yeah. Yeah, it's not taught in universities much anymore, right?
That's why we prefer Python. It's easier, less scarier.
Actually, one thing I want to do at some point is write a Python, or make it where you can implement materials in Python. Like make the C++ code call an external Python function where you can then write your material, get stress, get strain, or get tangent, get stress, given a strain and all that stuff.
Oh, that would be.
It's possible. It's definitely doable. I just haven't done it. I've done it with random variables, like where you can like call a Python random variable, or call out to Python to get your CDF, PDF, inverse CDF, all that stuff from the stats library. And it works. So, I mean, there's no reason you can't do it with Uniaxial Materials or other things. But
Faisal is suggesting something like UMAT in Abacus.
Yeah, basically, yeah. Same idea, yeah. So you won't have to like compile or do anything, right? It just you define a Python function and then boom.
So that would just pretty much I can run on my OpenSees, but someone else cannot use it until I give that piece of code to them, right?
Yeah. And we can do away with all these DLLs.
Less scary, at least. It would be
floating around, right? Yeah.
I guess if no other questions, then yeah, this will be the end of the session. Thank you, Dr. Scott, for the presentation. Hopefully, it will help a lot of other people who are trying to make their materials and help them make their lives easier. And we really appreciate your time.
Thank you. Yeah, I think if it doesn't make sense now, or you haven't done materials yet, I mean, this maybe come back to it when the time comes, and then hopefully this will get you off in the right direction, set in the right direction. So yeah.
I think it will definitely help people trying. So
okay.
Whoever, a couple of things, whoever, like we have the next session on Jan 8 from Jose Abel, I'll send out an email. And another thing is I sent everyone like a Google form to just fill in the details and say if you're interested to present in the future presentations and stuff. So please fill it and send it to, just fill it. You don't need to send it, but yeah, that would be helpful. Thank you.
Thank you.
Thank you.
Thank you.